Okay, there's a few things going on in Objective 2, Worksheet 2. One of them is just a continuation of how you evaluate a log. It really does go back to the idea of what power makes it work. Now, this is one of the few places where I'm going to actually create an equation out of this. I'm going to put equals x. In fact, I'm going to put equals x at the end of every single one of these log questions. Now, back in Objective 1, we used this idea of what power makes it work. Well, we're going to be a little bit more, defined and now. Because what we're going to do is we're going to take this problem out of its log form and into its exponential form. So you'll see by putting the equals x right here, what we're going to wind up, that x is going to be where the box used to be. So in a problem like log base 3 of 243 equals x, this is what the problem looks like in log form. In exponential form, the problem becomes 3 raised to some power equals 243. And that's really the biggest thing you've got to do right now is make sure you can go out of log form and into exponential form. Now, after playing around with your calculator a little bit, you'll find that 3 to the 5th power is 243, so 3 to the 5th equals 243, so that means x equals 5. In this problem, x equals 5. Now, for the next problem, I'm going to do the exact same thing. I'm going to take it out of log form and into exponential form. So that would be 4 raised to the x power equals the 5th root of 4. Now, I do have common bases, so all I need to do is now convert this radical into exponential form. And that would be, so I'm not going to touch the left-hand side, 4 to the x equals, the 5th root of 4 is the same thing as 4 to the 1/5 power. So now what that tells me is the value of x equals 1/5. Okay, moving on to problem 3. Same thing, I'm going out of log and into exponential. So in exponential form, this would read as 2 raised to the x power equals 1 over 16. Now, if I'm taking a nice whole number like this and turning it into a fraction, there's only one thing that'll do that, and that'll be a negative exponent. So I already know my exponent is negative. Okay, but 2 to what power would equal 16? And that would be 2 times 2 is 4, times 2 is 8, times 2 is 16. So it would be the 4th power. So, but 2 to the 4th power would be 16. I don't want 16. I want 1 over 16. So x must equal the negative 4th power. Now, the next problem. It's in log form right here. I'm going to take it to exponential form. So in exponential form, this problem would be 4 raised to the x power equals 0.25. Now, you got to think for a second. 0.25 is the same thing as 1/4. So this problem is really 4 to the x equals 1 over 4. So what power turns the number 4 into the fraction 1/4? and that power is -1. Now the last problem in this little section, I'm going to do the same thing. Notice I've done the same thing on every single one of these problems. I've taken it out of its log form and I'm going to put it into its exponential form. So 625 raised to some power equals 5. Now this one might not be as obvious, so we're going to do a little work. I need to get common bases. Okay? 625 can be expressed as 5 to a certain power. Play around with your calculator a little bit, and you'll see that 5 raised to the 4th power, 5 raised to the 4th power is 625. So that's what we're going to do. We're going to use the idea that 5 raised to the 4th power is 625. Okay? So I'm going to turn the number 625 into 5 to the 4th power. But when I raise a power to another power, I end up multiplying. So this would be 5 to the 4x equals 5 to the 1st. See, here's my 625 right here, hidden as 5 to the 4th power. But I had to do that, so I had common basis. Now that I have common basis, I can finish off the problem just with the exponents. So that means 4x must equal 1, so x must equal 1/4. My next 3 examples use the idea of what is called the common log. If you see a log expression, but you don't know what base it's in because it doesn't tell you, well, that base is base 10. So I've got 2 things to do on each of these problems. I'm going to do the first thing that I did to all the other problems we've done so far. I'm going to turn them into an equation by going equals x. Okay, so the next thing I'm going to do is I'm going to take them out of their log form and into exponential. Now, there isn't a number down there, so it's an invisible 10. You can put it there if you want, okay? But the first thing it's going to do is it's going to grow up. So we're going to go out of log form and into exponential form. So this is going to be 10 raised to some power equals 100. Remember, this is just where the box used to be, but now it's an x. So what exponent do you have to raise 10 to get the number 100? Well, it's 2. So the answer to this problem is 2. Now this one, okay? Again, there is no base shown, so we know it's a 10. So when we go out of log form and into exponential, it's 10 raised to the x power equals 0.001. Now we have to think about what that number is. That is 1/1000th. So 10 raised to the x equals 1/1000th. So there is a number, there is an exponent that will turn the number 10 into the number 1000. That's 3. Okay? But it's not 1000, it's 1/1000. So x must be -3. Okay, the last problem in this little set is what if, again, log, there's no number down there, so we're going to make it a 10, equals x. We're going to go out of log and into exponential form, so the little 10 is going to grow up. This is going to bounce over here, and that's going to bounce over there. You've done this dozens of times by now, going out of log form and into exponential form. So if 10 raised to the x is equivalent to 10 raised to the fifth, then that must be the value of x is 5. For my next 3 examples, I'm going to use something you might not be familiar with until this objective, and that is the natural log. We already know that a symbol that represents an irrational number, and that's pi. Well, there's another one in math, and that symbol is e. Now, it's not a variable. It's actually a symbol, just like pi is a symbol. It's called the natural log. The natural log uses the irrational number e. Now, it also has its own special notation. Anytime you're doing a log with e as its base, they don't write it like that. They write it as ln, natural log. So on the next 3 examples I'm showing right here, they're all written as ln, natural log, natural log, natural log. Okay. Now I'm going to do the same thing I've done with all the others. I'm going to put equals x, equals x, equals x. And then the next thing I'm going to do is the same thing I've done with all the others. I'm going to go out of log form and into exponential form. Now, there's just one little trick right here. Remember on this one, the ones up here, there was no number, and when we went into exponential form, the base became 10. All of a sudden, that invisible number became visible. Well, on this one, it's not a 10, it's an e. So, in exponential form, this looks like e to the x equals 1. So now I'm just using that special rule that anything in power form, and if you want it to equal 1, doesn't matter what the base is, any base raised to a power of 0 equals 1, so x must equal 0. Now moving on to the next one, the natural log of 1 over the cube root of e equals x. Okay, it kind of looks ugly, but the very first thing we're going to do is we're going to take it out of log form and into exponential. And since it's natural log, it means the base is e. So e raised to the x power equals 1 over the cube root of e. Now I'm going to leave the left-hand side alone. E raised to the x power equals 1 over. Now I'm going to take this out of its radical form. The cube root of e is the same thing as e to the 1/3 power. And so what takes this e down there, okay, it would be e to the 1/3, but it wouldn't just be 1/3, it has to get down to the bottom of the fraction, so that x is equal to the negative 1/3 power. The negative is what drops it down, and then I just need to match my exponents. Now the last problem, the natural log of the 5th root of e to the 7th equals x. So one more time, I'm going out of log form and into exponential, and since I'm in natural log, my base is going to be e to the x equals the 5th root of e to the 7th. Now, here's a good illustration of how to get out of radical form and into exponential. The 5th root of e to the 7th is equivalent to e to the 7/5 power. The index of the radical is the denominator of the fraction. And now I have common bases. So e to the x equals e to the 7/5. which means x must equal 7/5. Okay, the next concept, between what two integers will you find log base 7 of 2,000? Well, again, we're going to do the same thing we've done before. We're going to make it equals x, and we're going to go out of log form and into exponential form. So 7 raised to some power equals 20,000. Now, I'll tell you right now, there is no perfect whole number power that takes 7 up to the number 20,000. So what we have to do is we have to do a little guess and check with your calculator. Just have your calculator handy and start playing around with the powers of 7. Let's see what 7 to the 5th is. It's 16,807. So 7 to the 5th equals 16,807, which is below what we want. So let's see what 7 raised to the 6th power is. It's 117,649. So 7 to the 6th power equals 117,649. So 20,000 is between this number and that number. So the two integers, between what two integers will you find this? It's between 5 and 6. Okay, the last concept. Find the y-intercept for the following functions. Now remember, how do you find the y-intercept? By setting x equal to 0. So, y equals 3 times the log base 5 of, I'm going to substitute 0 for that x, 0 plus 25 plus 7. Now, next thing, y equals 3 times 0 plus 25 is 25. I'm just taking some really small steps. Log base 5 of 25 plus 7. Now, here's where we have to be able to start evaluating some of the more simple logs in our head. Y equals 3 times, what is the log base 5 of 25? Or you can go back to the first objective, what power turns the number 5 into the number 25? Well, the power is 2. And then plus 7. So all of this evaluates to be the number 2. Log base 5 of 25 equals 2. So now, y equals 3 times 2 is 6, plus 7 is 13. So there's your y-intercept. When x is 0, y is 13. Now the last problem, y equals log base 4, remember substitute x for 0, 0 plus 1 plus 6. So y equals log base 4 of the number 1 plus 6. So let's work on this part of the problem first. What power turns the number 4 into the number 1? And that is the power of 0, because 4 to the 0 power equals 1. Any number raised to the 0 power is 1. So this turns out to be the number 0 and then plus 6. So y equals 6. The y-intercept of this function is at 0,